Okay, so welcome to lecture number 5 for Stat 313. Let me switch my camera. So this is lecture 5. So today we'll be starting the introduction to hypothesis testing. We'll be discussing this in more details later, but here this is introduction to hypothesis testing. Okay, so let me just start by making some remarks regarding the hypothesis testing. I'm just trying to find a blue pen. Okay, never mind. So what is a hypothesis? So let's start by saying what is a statistical hypothesis. What is that? A statistical hypothesis is an assertion about the distribution of one or more random variables which we want to verify on the basis of a sample. You'll see a lot of examples, right? Like this one. So there's the assertion that a random variable, for example, it possesses a normal distribution, or suppose the assertion that the mean of a Poisson distribution for this random variable is 2, that is a statistical hypothesis. Okay, so example that X follows normal distribution. Okay, or maybe it's known. Suppose we know X follows a Poisson distribution with some parameter lambda. The hypothesis is lambda equals to say 2. Okay, so these are all the examples, or these are some of the examples of statistical hypothesis. Now, what do you do in this lecture is we'll be testing the hypothesis. It's called the test of hypothesis. Okay. It goes like this: a test of a statistical hypothesis is a rule which when the sample values have been obtained, leads to a decision. So it leads to a decision to accept or to reject the hypothesis under consideration. Well, again, it may be a lot of word at this point, but later on you'll see concrete examples. So it may make much more sense then. Okay. So what we is a test? So it's a test of hypothesis is the test of a statistical hypothesis is a rule, which when sample values have been obtained, it leads to a decision. So either to accept or reject hypothesis. Okay. Um, Roughly speaking, in relation to the previous chapter, what it means is that so once again, example. Last lectures, it gives us how to sort of have we have a random variable, say x, with the distribution f of x, which is dependent on some parameter theta. We have done this, where theta is in say omega. Okay. Now suppose we think, now we have seen a way to find the confidence interval for omega and many other things in the previous chapter, but here the objective is a little different. Okay, so suppose we think that this theta, it belongs to maybe say omega sub 0, or this theta may belong to some omega sub 1, where this omega sub 0 and omega sub 1 are disjoint subsets of omega. In other words, what I'm disjoint, so what I'm trying to do is, so here's my omega. So suppose this is my omega 1, this is my omega 2. So where omega 1, omega 2 is null, and omega 1 union omega 2 is the omega. Okay. Now the question is, so roughly speaking, what it means is this theta can be anywhere here, right? But suppose we have reasons to believe that for some reason theta is either in omega, oh sorry, this is omega 0 and this is omega 1. Sorry, so it's let me change this to 0. Yeah. Okay. Now the question is where. Okay, so so the question is, where does omega lie? So the hypothesis that we're testing here is omega. So this theta is either in omega 0 or theta is in omega 1. Actually, that will lead to my next definition. So let me just write the next definition and then we'll explain. So here's a very important definition for this section. It's the null hypothesis and alternative hypothesis. Okay. So what is a null hypothesis? A hypothesis which we set up and proceed to test with the help of the sample observations is called a null hypothesis. Versus any hypothesis that contradicts the null hypothesis is called an alternate or alternative hypothesis. It's a lot of definitions which we'll be using throughout this course. um, according to Fisher, one of the greatest all-time statistician. So what is a null hypothesis? So according to Fisher, a hypothesis which is tested for plausible rejection under the assumption that it is true is a null hypothesis. Okay. And okay, so we'll be discussing this. So back to the last example. What was that example? I'm talking about this one. So suppose we are checking distribution of say f of x by distribution. I mean, it's really the PDF. Okay. So the way I wrote it, it's so density. Otherwise, it'll be confusing. Okay. So suppose this is what we started off with. So suppose we say theta is in omega 0 is our null hypothesis. What will be the alternate hypothesis? Well, theta is not in omega 0, so that means that ought to be in omega 1. So theta is in omega 1. Okay. So it's written as, by the way, so this null hypothesis is written at a sub 0, and alternate hypothesis is written as a sub 1. Okay, that's a very universal notation of this one. So H0 would be theta is in omega sub 0 versus H1 is theta is in omega sub 1. Okay. For the last example, that those are the null hypothesis and alternate hypothesis. Okay. Okay. Let's see. Now, I'll be defining some of the terms using words, and then I'll be defining those things using some mathematical notation. Okay, let's get this done first, because otherwise later on we have to again come back and redefine it. So I want to do all the definitions at the beginning, and then we'll study some examples. Otherwise, it'll be going too much back and forth. So I understand it may be a little boring at the very beginning, but please follow this carefully, because this helps. Okay. All right. So let's see. Now, let's define something called a critical region. Critical region. All these things will make much more sense when later on we'll be doing some examples. Okay. So how do you define the critical region? Suppose I'm just thinking that probably it's a good idea to. Okay, before critical region, let me just define something called sample space. Or the space of sample. Let a random variable x as a sample given by, sorry, this is let a random sample x1, x2, xn. So it's a sample of size n be drawn. By the way, this is my x. Okay, so it looks odd. Drawn from a population. If we draw so according to my notation, please excuse me for this one. According to my notation, so this is the notation for the random sample. this is general notation for the random sample, right? So let x1, x2 be xn be the observations. Meaning that suppose we observe this one, so this random variable x1, big X1 is taking the value x1, random variable x2 takes the value x2, random variable xn takes the value xn, right? Now what happens is if we draw another random sample of size n observations, it'll be usually different, right? So let me just write it. So if we draw another sample of size n from the same population, the sample observations are usually different, right? It may be, say, x1 prime, x2 prime, xn prime, where x1 prime is coming from this random variable x1, x2 prime is from x2, and so on. Now considering an n-dimensional space, if we plot such sample observations, we'll get different points for different samples. Okay. We get bunch of samples, right? Now the collection of such points corresponding to all possible samples is called a sample space. Okay. So the sample space here is so the collection of such points corresponding to all possible samples is called a sample space. Okay. So now this sample space maybe it may be I mean, so in this case we have all this bunch of numbers. So we have n numbers for a sample. We just dump all possible samples in that set, and we call the sample space, or it's called I think more appropriate it's space of sample. Okay. Let me just write it as a space of sample. Sample. Okay, its notation in the book, they denote it by D, a curly D. So basically, this is the space generated by all the random variables x1, x2, xn. Okay. So you see all the samples, and whatever you observe, so just dump it there. So that is the sample space. That's all possible value of the sample observation. Okay, so with this, now I'm ready to define the next one, which is called the critical point or critical region. Once again, as I said, that I'm spending much time here for defining terms, which will be super useful throughout the course. Okay, now let C be a subset of D. What is D? This D. So let C be, which C is the is a subset of D. So the space of samples. So I'm taking a subset C of D. Okay, such that what is the speciality of the subset? Such that we shall or we will reject H0. The hypothesis will reject the hypothesis, the original hypothesis, null hypothesis, if the observed sample point x1, x2, xn falls in falls in C, and accept H0 otherwise. That means when the observed value falls in the complement of C. Then this region, then C is called the critical region. And also the C complement, so C complement is, so if you see that this is the set D, so you have C here, C complement, C, this little C means complement. Okay? C complement is also called the region of acceptance. It may be very abstract at this point, but believe me, I mean, it'll be more concrete pretty soon when we do a bunch of examples. Okay. I need to write this in a more mathematical way. So basically what we say is reject what I wrote here. It's in summary, it means reject H0 and accept H1 if the sample x1, x2, xn is in C, and retain. So this is reject or retain H0, or in other words, reject H1. Remember, H0 and H1 are like H0 is a null hypothesis, and H1 is the alternative hypothesis. The alternative hypothesis is something that that contradicts H0, right? So we reject we retain H0 and reject H1 if it belongs to the complement. So if x1, x2, xn, it belongs to the complement of C. All these things will be very clear when we do some example. Okay. Now, with this in mind, let's write one more thing. For the test, we'll be testing the hypothesis, so we'll be using some test criteria, which will be called a test statistic. What is a statistic? We have done this before. We have discussed this before. This is a number based on the So what is statistics? So it's the number based on the sample values. Okay. So it is a statistic. In other words, that is a function of the sample values, which is used for formulating a test you'll see what it means. For example, we'll have this test statistics test statistic in terms of the z or the t distribution. Okay. All right, so that is pretty much it. And now I'm ready to define. So now we have two hypotheses, right? So there can be two different cases. So we can have this table. This table is very handy. So suppose this is the true state of nature. Okay. So suppose somehow you know that the true state of nature is H0 is true, or the true state of nature is H1 is true. Now you have some sample. Again, it may be very abstract, but we'll make it concrete very soon. But suppose this is the state of nature. This is a real state of the nature, true state. Okay. And what is our decision? So here is a decision after we perform some statistical test. Suppose we reject H0 or accept H0. These are the two possibilities, right? Now look at this, the first case, where H0 is actually true but we actually rejected H0 after our test. So we made some error, right? This error is called a type 1 error. Alternatively, if H1 is true, so that means H0 is not true, but we accept H0, we make another kind of error. This is called type 2 error. Okay. These are the two erroneous decisions. Now, suppose, let's come here. H1 is true, that's the exact state of nature. And we rejected H0 in favor of H1. So that means it's a correct decision, right? Here, H0 is true and we accepted H0. That's also a correct decision. So basically, there are two different kinds of errors. One is a type 1 error, another one is type 2 error. So type 1 error is the case when H0 is true in reality, but we reject H0. And type 2 error is the case when H1 is true in reality, but we accept H0. Okay. So let's define this properly, because these are sort of two central ideas of the hypothesis testing. Type 1 error. This is the error committed in rejecting H0, which is the null hypothesis, when actually it is true. Okay. So basically, we'll have a way to compute it. We'll see how to understand it and how to compute it. And the second one is type 2 error. Well, actually, we'll not compute it. We'll somehow bind it with a range. Okay, so this is the error committed in accepting H0 when actually it is false. So please note these two things. So the first one is rejecting H0 when it is true, and second one is accepting H0 when it is false. Okay, so this is basically what we showed in this table. Now, if I want to write this mathematically, so basically, probability of the type 1 error is the probability of rejecting H0 when it is true. So how do you get that? So basically, it's probability of your sample, whatever you have the sample. So say x1, x2, xn. So that got to belong to the critical region. Remember what is a critical region? So critical region is the region if your x1, x2, xn if that belong to a C, then we reject that. Okay. However, this is under the assumption that the null hypothesis is true, so it's given H0. So one way of writing the probability of type 1 error is your sample belongs to critical region, but actually H0 is true. Well, again, don't worry too much. We'll be discussing this in more details when we do some examples. And what about the probability of the type 2 error? So probability of type 2 error, I can write this as, so this is basically probability of accepting H0 when it's false, right? So that means I must have probability of accepting H0. So when can we accept H0? So that means, or retain H0. That means x1, x2, xn belongs to C complement, right? So that means we have x1, x2, xn complement is in C. Sorry, this in C complement. However, H1 is true. Okay. So this is the probability of retaining H0, but when actually the true thing is H1. Another way of writing this is basically 1 minus probability of x1, x2, xn is in C. Okay, so I can write the C complement, I can change it to C, and I write 1 minus where H1 is true. So this is the probability of type 2 error. Okay. Look at these two expressions. So this one, probability of x1, x2, xn is in C, where H0 is true. And here, it's 1 minus probability of x1, x2, xn in C, where H1 is true. They're fundamentally different. Okay. The way it's written is the complement of the probability of the type 2 error is called the power of the test. In other words, this, what I wrote here, is called, so this quantity is called a power of a test. Of the test, this quantity, okay? All right, so we have a bunch of definitions. So probability of type 1 error, we write this way. Probability of type 2 error, we write this way. And this part is called the power of the test. I'll define it more formally very soon. But this is sort of the first step, okay? Okay. let's write this little bit in more carefully because later on we'll be just using this a lot without much explanation. So it's a good time so that we can go slowly, and we may spend some time explaining these concepts. Okay. Okay. Um, now we have the critical region, right? So we already defined the critical region. So critical region is a region. So if somehow the sample values are in this region, we reject the null hypothesis. So that's the deal. Okay. So now, what is the probability of rejecting a null hypothesis? Okay. Or what is the, if we say that, what is the size in code? Can we define a size of this C? So here is another definition. It's called the definition. We say a critical region. Again, critical region means the region for which will be rejecting the null hypothesis, right? Region C is of size alpha if alpha is the maximum value x1, x2, sorry. So it's a maximum of probability x1, x2, xn in C. Okay, I'll explain this maximum thing, but let's see. Okay, so think about it. So the probability that x1, x2, xn is in C, right? So we have seen that we have so many uncertainties. For instance, of course, if I specify a value of theta, so remember this, there is a probability density function that depends on theta. Okay. So if that is known, then this is the number. So this is the quantity that I computed right here, right? So probability of x1, x2, xn in C. Okay, but theta is usually unknown. So remember that that is why we need this whole set of null hypothesis and alternate hypothesis. So the theta value. So if theta goes here, then that is our null hypothesis. And if theta goes here, that is our alternate hypothesis. The value of theta is not known. That's a problem, right? So that's why now when this quantity, this sample is in C, but this sample inherently depends on theta. Okay, or whenever you compute this probability, sorry, not the sample. The sample is a sample, but this when you compute the probability, that inherently depends on theta. So in order to show the dependency, we sometimes write P sub theta. Okay. Now this theta can be in omega 0. This theta can be in omega 1. Now this is the maximum for when theta is in omega 0. Now if it's too technical definition, you may skip this for this course, but I'll be mainly using examples, but this is the actual definition for the size of alpha. So out of all thetas in this omega 0, I'm taking the one that maximizes the probability. Okay. So in other words, it says that over all critical regions of size alpha, we want to consider the critical region that have the, after we compute this, so this is of size alpha critical region. And then what we'll do is over all critical regions of size alpha, we'll consider the critical regions that have the lowest probability of type 2 error. Okay. We'll do that, and you'll see how we do that. But let's see. One more thing. So that means we can write the probability of type 2 error is 1 minus p theta over x1, x2, xn in C, provided that is theta is in omega 1. So theta is in omega 1. This is another way of writing the same thing, which is written here. The probability type 2 error, I wrote it before this way. So what is the difference between this notation and this notation? So here we specify H1, but H1 another way is basically theta is in omega 1, right? So that takes care of this one. So another way of writing the same thing. Writing what we wrote before. Okay. Why I wrote this? Because this involves the power of the test, right? So power of the test means, remember, so here this quantity is the power of the test. So if you combine, so essentially this is the power of the test. So the power of the test, is given by, in this notation, it's p theta, basically this one. So it's x1, x2, xn in C, where theta is in omega 1, and we'll write this usually as gamma c of theta. That's a common notation for the power of the test. Essentially, I wrote the same thing as before. So the only difference is here I wrote when H1 is true, and H1 is true really means theta is in omega 1. Okay? So that's another way of writing the power of the test. Okay. This is all. So we are done with the definition. At this point, let's see if we can solve some problems, okay, with all this. Okay, I know that this is a little bit a lot of information at the very beginning, but it's required because, and I would definitely want you to go over this again and again, so until you sort of be comfortable. But I can promise you that after you have gone through the following examples, this will, if you go back here and try to understand this one, it'll make much more sense. Okay, so at this point, it is just a definition, but it'll make much more sense after you have gone back, after you sort of solve the examples and see these definitions. Okay, let's do this one. So example, let's see. In order to test, or in order to check whether a coin is perfect, the coin is tossed 5 times. Okay. The null hypothesis, so the null hypothesis here is the coin is perfect. I'll write it. But the null hypothesis of perfectness is rejected if and only if more than say 4 heads are obtained out of 5. Question is, what is the probability of type 1 error? This is the first part. Second part is find the probability of type 2 error when the corresponding probability of head is equal to 0.2. Okay, so what is the null hypothesis here? Null hypothesis is the probability of head is 0.5. So what should be the alternate hypothesis? Type 2 error is related to the alternate hypothesis. So it should not be 0.5. So in this case, we chose 0.2. Okay, let's solve this. So solution. All right. So let x be the number of heads obtained in 5 tosses of the coin. Okay. And p, so x is the random variable, that is the number of heads. Okay, so p is the probability of the head. So probability, so p of h, so little p. Okay, so then in general, so then the probability mass function, x is the number of heads, so x of x is given by, the probability of big X equals to, suppose it takes value little x. So that means there are little x number of heads out of 5 heads, out of 5 tosses, right? So how do you compute it? So it's basically binomial distribution. So it's for 5, choose x, p to the x, 1 minus p to the 1 minus, 5 minus x, right? For x can be 0, 1, 2, 3, 4, 5. For these 5 values. X can be no, there can be no head, there can be 1 head, all the way up, there can be 5 heads. Okay, so let's write now this. So here, H0 is P equals to 1/2. So we are testing if the coin is fair. So P is 1/2. Now, what is a critical region? So by the way, H1 is P is not equal to 1/2. So that's the hypothesis, that's alternate hypothesis, right? Now, critical region. The critical region is x is bigger than 4. Why? Because that is the region. So if we observe x to be bigger than 4, that is our decision rule, right? So the null hypothesis is rejected if and only if more than 4 heads are obtained. So that is the region we call the critical region when we reject the null hypothesis. So the critical region is obtained for x is bigger than 4. That is, so since we have just 5 like tosses, so that means x is 5. Okay, so that means if we see 5 heads, then only you reject the hypothesis. So so now let's go back. So the probability of type 1 error is what? So look at this one. I wrote it before. It's probability that x is in the critical region. In our case, so the critical region is x got to be 5, and we don't have. So we can only see that x equals to 5. And what is H0 under the assumption? Here, H0 is P is half, right? So type 1 error is probability of x equals to 5 given H0, right? So that means probability of x equals to 5 given P equals to 1/2. And now we have this formula, P probability of x equals to x is this one for a given P. So it's really 5 5 choose 5, which is 1, 1/2 to the x, which is 1/2 to the 5, and then 1/2 to the 0. So it's really 1/2 to the 5th power, which is 1/32. So the probability of type 1 error is 1/32. That's answered. Okay. All right, so we are done with the first part. The second part is, what is the probability of type 2 error when the corresponding probability of head is 0.2? So let's compute this. So the probability of type 2 error is basically probability. I mean, we have written in many different ways. So we wrote it that 1 minus, I mean, this is fine. This is equal to 1 minus probability of that the value is in the critical region and given H1 is true. So I can write this as 1 minus probability of x equals to 5, because that is a critical region, given the alternate hypothesis, which means 1 minus probability of x equals to 5, given, in this case, it's also given that the corresponding when the corresponding probability of head is 0.2, so it's given. So that means I can write this as probability of 0.2. Okay, so here it is going to be 1 minus 0.2 to the 5, just like the previous computation. So if you compute this, it's basically 1 minus 5 to the 5. So this is 3124 over 3125. That is the answer. Okay. So this is the probability of type 2 error when the corresponding probability of head is 0.2. So for this corresponding probability of head, it's the answer. Of course, if your probability of head, if something else, this result will be different. So whatever the corresponding probability is, it's based on that. Okay. Next. So this next example. um, let's see. Since we're doing the coin example, so let's do one more for the coin. A coin is tested for unbiasedness. The hypothesis, that means if the coin is fair or not. Okay? The hypothesis that it is unbiased is rejected. Hypothesis means it's a null hypothesis, rejected if 9 or more tosses of the coin out of 10 tosses result in head. Okay, so that's the deal. Now the question is, can we take 1% as level of significance? Okay, that is a question. By the way, I just realized that I forgot to mention what that level of significance is. I wrote it. So this alpha here, which is the size of the critical region, it's also called the level of significance or the significance level. So this is also the significance level of the test. Significance level or level of significance, they're the same thing. So that is basically that alpha. So what is that? How do you understand the um, level of significance? Okay, it's basically the upper bound of the type 1 error, isn't it? So it's a maximum value. So remember that this is giving you a type 1 error, right? So when maybe theta is known, but usually theta is unknown. So this type 1 error, based on whatever the theta is, it changes. Whatever the maximum error, maximum of this one, so that is we call alpha, right? So this is really the maximum value of the type 1 error, right? So this is maximum value, note. It's the max of type 1 of probability of type 1 error, right? Or in other words, it's the upper bound of the probability of type 1 error. That's the size of the critical region, right? Okay, so now let's go back to this problem. So the question is, we have this nicely designed test. Can we say that 1% or alpha equals to 0.01 is a level of significance? Let's try to answer this, and we'll learn something when we try to solve this. Okay, so let just like in the last problem, so let X denote the number of heads obtained in 10 tosses of the coin, and little p is the probability of the head, just like the last problem in a toss. So therefore, probability of X equals to little x, just like the last problem. So except here, in the last case, I believe we had 5 tosses. Here we have 10 tosses. So it's X, choose 10, p to the x, 1 minus p to the 10 minus x. It's a simple binomial distribution. So it's x, it can be 0, 1, to all the way up to 10. Right. So the null hypothesis, hence, the null hypothesis is the coin is fair. H0 is p is 1/2. And H1 is p is not half. Okay. Now let's compute the probability of type 1 error in this case. So what we have here is the following. So when we have this test, we can very well write the probability of the type 1 error. Let's first identify the critical region. So the critical region in X. So what do you need? So we can reject if 9 or more tosses of coin results in head, right? So so X can be 9 or more. So that means in our case, it should be either 9 or 10, right? So X can be 9 or 10. So what is the probability of the critical region? So I'm trying to see how I wrote this in the last problem. So the last time I wrote this one, right? Probability of type 1 error equals to this one. So let's use the same notation. So probability of type 1 error is equal to, so probability of X can be 9 or X can be 10 given the null hypothesis is true. Okay, so that means it can be either 9 or 10, right? So if it's 9, what is the probability? So the probability is 10 choose 9, 1 over 2 to the 9, 1 over 2. And the other case for x equals to 10, it will be 10 choose 10, which is 1, and 1 over 2 to the 10. So if you compute this, it's basically it's 10 plus 1, which is 11 over 2 to the 10, which is about 0.0107. So that is the probability of type 1 error in this case. Um, now, please note that what was the problem? The problem given here is, can we take one person as the level of significance? We get the probability of type 1 error is 0.0107, which is more than 0.01. But we know that the level of significance is the maximum probability of type 1 error. But we observe that here, whatever we got, it's more than 0.01, right? And hence, the probability of type 1 error, well, let me just write the reasoning too. But the level of significance is the upper bound of the probability of type 1 error. Hence, we cannot take 1%, which is 0.01, as level of significance. Okay, done. Okay. All right. So let's now solve another one. Example. So this goes like this. Suppose given, say, f of x equals to 1 over theta, where 0 less than x less than theta, and 0 otherwise. Basically, we are talking about an uniform distribution, okay? So basically, we have a uniform distribution between 0 and theta. So the value is 1 over theta, okay? Test the hypothesis. H0, which says theta is 1, against alternative hypothesis, H1, which says theta equals to 2, on the basis, I mean, we cannot just test the hypothesis, we need some sample, on the basis of the single observation X. Okay. On the basis of one observation, we have to test this hypothesis. We'll see how. Okay. Of course, this is not final, so find the probability of type 1 error and type 2 error. If the critical region Bx is more than 0.5. So we are specifying a region when we'll reject the hypothesis, which is a critical region. So maybe x equals to 0.5 is somewhere. Please note that this theta can be more than 1. Okay, so it can be anywhere. So x more than 1, more than 0.5 will be, so that is our critical region. And what we'll do is we have one observation, and based on that, we have to conclude if theta equals to 1 or theta equals to 0. So that's the deal. Okay, let's solve this one. So here is a solution. All right. So here the null hypothesis H0, it's written, but let me just write it here. Against the alternative hypothesis is theta equals to 2. So the PDF, the probability density function under H0 is fx equals to, so the probability density function was given by fx equals to this one. So given the PDF is given by this one. So fx, if I just replace theta by 1, it will be replaced two places, here and here. So fx equals to 1 for 0 less than x less than 1 and 0 otherwise. And for this one, so PDF under H1 is fx equals, so now if I have theta equals to 2, it's 1 over 2 between 0 and 2 and 0 otherwise. So f theta equals to 1 over 2 between 0, x less than 2 and 0 otherwise. Okay. And the critical region is given to be x is more than 0.5. So the probability of type 1 error is basically probability that my value is in, so the random variable x is in, so this is for x. So this is a value of this is a PDF of a random variable x. Okay. So what is the type 1 error? So my x got to be more than 0.5 under the null hypothesis, right? So under H0. That's the definition. Remember? So this is how we define the probability of type 1 error. So x, so there, I mean, this is for the sample, but I'm concluding based on a single sample, right? So based on a single sample, so x should be more than 0.5 given H0, right? So it's going to be, in other words, this is basically x is more than 0.5 with respect to theta equals to 1. That means I have this entire probability density function, so I can basically integrate. So it's basically 0.521. The value of the function is maximum is 1. So it's 0.121. And then in that room, it's 1 dx, right? With respect to theta equals to 1. So I'm integrating the PDF between 0.5 and 1. So this is something we have done from the, you must have seen how to do it. So it's basically x in the limit 0.5 and 1. So it's 0.5. That's the answer. So probability of type 1 error is 0.5. Okay. Now the probability of type 2 error is essentially, I mean, we can of course do it 1 minus that way, but let's just do it straightforward way. So and by that, I mean, let's at least one problem do it this way. Probability that the single observation in this case, we don't have n, we have one observation. So it's x is in the C complement. What is C complement? So that means your x should be less than or equal to 0.5 with respect to H1, right? So we can write this x is less than equal to 0.5 given H1, right? So that means we want this probability of x is less than 0.5 given theta equals to 2. And now I can compute this probability for theta equals to 2 because I know the PDF. So this is going to be the PDF is 0 to 0.5, 1/2 dx, right? So if you compute this, it's 0.25. So that is the probability of type 2 error for this problem. All right, so these are some of the examples when you can compute the probability of type 1 error and probability of type 2 error based on the observation. Okay, let's now consider one problem that is given, that's actually discussed in the book. So let's continue with that. So what kind of problem is that? And that is actually a very common hypothesis testing problem. It goes like this. Example. So it's called the large sample test for the mean. We'll see what it means. It goes like the following. It takes let x be a random variable with the mean equals to mu and finite variance sigma squared. We want to test the hypothesis. We want to test the hypothesis that H0 is mu equals to mu0, where mu0 is a specified value, a fixed specified value. For instance, you can think this said 5. Okay? So we are trying to test if mu equals to mu0 versus, it's sometimes written versus, sometimes against, whatever, or just write it after some space. H1 is mu is bigger than mu0. So for instance, if your mu0 happens to be 5, the hypothesis is mu equals to 5 against H1, alternate hypothesis is mu more than 5. Okay. All right. Now here we don't specify, so x is a random variable. It's not necessarily random, right? But we can do some large sample approximation in the sense as we have done in the previous cases. Okay. So here is what we'll do. So here's the procedure. Let us draw some samples from this x. Let x1, x2, xn be a random sample from x. Okay. And then sample mean, as we have dealing with, sample mean is given by x bar, and sample variance is given by s squared. Okay. So these two are very common as we have done before. So we have sample mean, we have sample variance. By the way, sample variance means that you're dividing by n-1. Okay, so remember that. Okay, now note that this we know. So we have seen that E of x bar is really mu. So here is an aside. This does not depend on the fact that, no, I mean, we don't even need the normal distribution for x, right? This is true all the time. So the sample, this is called the sample mean, is an unbiased estimator for population mean. Again, by population mean, I mean mu, and sample mean, I mean x bar. Okay. Okay, so X bar is an unbiased estimator for mu. So then the decision that, okay, the question is your sample mean is close to mu zero, or it's equal to mu sub zero. So an intuitive way, uh, guess, or intuitive way decision rule can be, well, if X bar is kind of far away from this mu zero. So you have mu zero and you have X bar. So if this X bar is kind of very far away, I'm making it very vague, but suppose this X zero is far away from mu zero, then we reject our hypothesis that mu is mu zero. But if this X bar is close to mu zero, then we can, then we are good, right? So here's an intuitive way that reject H0 in favor of H1 if X bar is, now let me put it in quote, much larger than mu zero. Of course, it's not quantified. Much larger can mean anything. Okay. So now let's try to quantify it. And that will lead us to the so-called um, estimation using some, I mean, you'll see all these abstract ideas in play here. Okay. Let's see. We have seen, now I'll try to formalize it. We know by central limit theorem uh, for large sample, that means when n is large, then this distribution I can write, say, X bar minus mu over S over square root of n. This is basically X bar minus mu over S. So this is following a normal distribution. So this is approximately the standard normal. Okay, so that's the content of the central limit theorem. Using this, so let's using this, using the fact that this follows approximately a normal distribution, using this, we construct a test. Now I'll design a test of hypothesis with approximate size or significance level. So I think so that is something we are discussing. I think we encountered this term some time back. Let me just show you quickly here. So we have significance level, that alpha, that's a maximum bound for the type 1 error. The approximate size or significance level. Alpha with the decision rule. Once again, what is alpha? So alpha is the cases when we'll reject the null hypothesis. So that means X bar should be in quote far away from mu, right? So here's the decision rule. Reject. So here's the decision rule. Reject H0 in favor of H1 if this test statistic that we constructed, X bar minus mu 0. Sorry, by the way, so here this got to be um, mu. So basically, what we are saying is now this mu is approximated by. So this mu is the population mean, and we are saying that okay, under the null hypothesis, this mu is mu zero, right? So, and remember this approximate size of alpha, everything is with respect to the null hypothesis. So this is with respect to h0, and hence we write mu zero. Okay? With respect to h0, mu is mu zero, right? So this is over s over square root of n is bigger than some z of alpha. So once again, what is z of alpha? So if I have the z distribution, so this is, if this level is alpha, this point is called z of alpha. In other words, phi of z of alpha, phi is the CDF of the standard normal distribution. So this is basically 1 minus alpha. What we are saying is, if this statistic value is more than z alpha, we reject it. So that means x bar and mu zero are not close together. And in that case, we say that, I mean, that is our decision rule. Let's see. Can we define or can we find a power of the test in this case? So let's find, so this is the decision rule. We'll do some examples on this one later, but let's see if we can if we can compute the power function. Suppose suppose we know the exact, the value of sigma. Okay. Then basically we can replace this as s by sigma. So what is the power function? So the power function is gamma of mu. Let me show you what we wrote before so that you can compare. So here is what we had, the power function. So here the unknown theta, so that is our unknown parameter. So in our case, that is simply mu, right? Okay, so that is what is the confidence interval? So confidence interval is when so when this value, so basically this really gives me x bar is bigger than mu zero plus z alpha times s over square root of n. So that is the meaning of this previous sentence, right? So that means this is a critical region, and I want this critical region to be true under the alternate hypothesis. Okay, so and what is the alternate hypothesis? So because the value of mu is not mu zero. So now this is going to be probability. So this is the probability of say x bar is bigger than mu zero plus z alpha sigma over square root of n. Sigma, I wrote sigma because now in our case that we know sigma. Okay, so we replaced s by sigma. Okay, so can we compute it? It turns out yes. So let's write this probability of x bar minus mu over sigma over square root of n is bigger than mu zero minus mu. I'll leave this computation to you. Sigma over square root of n plus z alpha. Okay. One more thing, please note that whenever I'm doing this power up test, so it's always with respect to h1, right? And that's why I did not write mu zero here. Okay. Just compare this with what we had here. So here, when we are computing the significance level, so we had this mu sub zero, and here we are just writing mu. Okay. Now, this quantity is approximately normal. So I can write this as Well, first of all, this is 1 minus probability of x bar minus mu over sigma over square root of n less than mu 0 minus mu over sigma over square root of n plus z alpha. I'm just shifting this inequality. And this is approximately 1 minus normal, the standard normal distribution for this one, right? So it's basically z alpha plus square root of n mu 0 minus mu over sigma. Okay. Please note that one more thing. So this is from the normal distribution. So if we have something like this one, so if you have, say, I don't know, beta, so 1 minus phi of beta, that means this area, right? So phi of beta is this area. So 1 minus phi of beta is really this area. I can also write the same area as it's a symmetric figure. So it is same as phi of minus beta. Check it. Isn't it true? So 1 minus phi of beta is this region, this unshaded region. Using symmetry, phi of minus beta is the unshaded region would be something like this one, which is same as this one. So this is phi of minus beta. These are two different regions, but their areas are the same. So these are true, right? So this quantity, I mean, again, this is just calculation, but you can also write this as phi of whatever you have, you just write negative sign of that. So it's minus z of alpha minus square root of n mu 0 minus mu over sigma. So we designed a test. So we successfully designed a test, which will be, we'll be doing some example later, but it will be computing. So you're given a sample. The question is, can we say that the mean is equal to mu sub 0, a particular number, versus mu is not equal to mu is better than is bigger than that mu sub 0? Using this test, we should be able to address it. And these are, when we will reject it, when what is a power of test, everything is now understood. Okay, so I went pretty slowly today, but I think this is a good place to stop. So what I'll do next time is I'll be picking up from this point, and we'll be considering some more examples, and we'll be building on this particular example, and we'll be continuing with this example, and we'll be discussing some more examples next time. So that's the plan. Okay, I'll stop.